In this video, I'm going to answer questions under fluid mechanics. I'll be very fast. In our first question, we are creating the weight. So we know that weight is equal to pressure times area, or force is equal to pressure times area, which is equal to 20,000 times 4 tires times 0.024. So our weight is equal to 19,200 newtons, which is equal to 1.9 times 10 to the power 4 newtons. So that's our final answer. That's our solution. In our second question, we've been told to find the absolute pressure. So absolute pressure is equal to atmospheric pressure plus density times gravitational force times height. So that's the formula for the absolute pressure. So pressure is equal to 1,001,300 pascals plus 1,024 kg over 1 meter cubed, 1 meter cubed times 9.81 newtons over 1 kg times 1,000 meters. So that and that will cancel, and that will go. So pressure is equal to 1,001,300 pascals plus 100,045,440 newtons per meter squared, which is equal to 10,146,740 pascals, which is equal to 1.01 times 10 to the power 7 pascals. So that's the solution. That's the absolute pressure. For our third question, let us draw the diagrams of the YouTube before water was poured in and afterward. On our left hand side, we've got the data, and we've been told to determine the length of the water column in the right hand of the YouTube. So when you look at the first diagram, the dotted line, they're representing the level of mercury before water was poured in. And in the second diagram, the outlined lines, they're representing the lines of mercury, or the level of mercury after water was poured in. So that represent the height of water column. So that's the length of the water column. And then, okay, so let us label those points as x and x prime. Then that is going to be our h1, so that height is going to be our h1. And then we are also going to have our h, the height of the mercury from its original level. So we know that volume is equal to area times height. So volume is mass over rho, which is equal to 5 times height. So the length of the water column is equal to mass over density times 5. So the density of water times 5. So the length of the water column is equal to 100 over 5, which is equal to 20 centimeters. So 20 centimeters is the height, or is the length of the water column, 20 centimeters. So that's the final answer. And then let's go to question 2. So distance h of the mercury lies in the left arm. So we are going to say h1 is equal to h. When you get that, it's going to give us h1 is equal to h. Then we are going to say pressure 1 is equal to pressure 2, because it's balanced. So pressure 1 is atmospheric pressure plus density rho over mercury times gravitational force times h plus h1 is equal to atmospheric pressure plus density of water times gravitation times height. So let me write it here. Atmospheric pressure plus density of mercury times gravitation times h plus h1 is equal to atmospheric pressure plus density of water times gravitation times HW. So density, so atmospheric pressure we know, it's going to cancel. So we're going to have 13.6 times 9.81 times H plus H2H is equal to 1 times 9.81 times 20. So atmospheric pressure on both sides is the same, so it's going to cancel out. So this is equal to 13.6 times 3H is equal to 20. So our H is equal to 20 over 13.6 times 3. So 0.49 centimeters. So that's the height or the distance H of the mercury. So let us do another question. In this question, we've been told to find the force required to completely submerge the ping pong ball under the water. The ping pong ball is having the density of 0.084 grams per centimeter cubed, which is less than that of the water. So our diagram is this. So a ping pong ball under the water, and then that's a level of water. So the forces acting on this is weight, and then the force applied and the buoyant force in the opposite direction, upward direction. So weight plus force is equal to buoyant force. And we know that weight is equal to density times volume times gravitational force. So we're going to replace weight by that. So it's going to be rho Vg plus F is equal to density of water times volume times gravitational force. So our force is equal to density of water times Vg minus density of the ball times Vg. So we know that Vg is the same, going to come out, and then density of water minus density of the ball in the brackets. So that's the formula. So now let's find the force. So we know that the volume is going to be 4 over 3 by r cubed. So that's the sphere times 9.8. 1 minus 0.084. Okay. So if you have a sphere, the volume for the sphere, the formula is 4 over 3 by r cubed. Okay, a ball is a sphere. That's where the formula came from. Or that's where we got the formula. So our force is equal to 4 over 3 times pi times our radius is 1.9 times 10 to the power negative 2 cubed times 9.8 times 0.916. So this is equal to 257.9 times 10 to the power negative 3 newtons. So that's the force required. So the force is equal to 0.258. So that's the solution, 0.258. And then I will get another question. So locating the speed at which the water leaves the hull. So velocity is equal to square root of 2gh. So velocity is equal to square root of 2 times 9.8 times the height of 16. So that's 16. So which is going to give us 17.7 meters per second. So that's the speed at which the water leaves the hull. Then our question B, the diameter of the hull. So diameter, area is equal to V, which is the volume over velocity times time, is equal to 2.5 times 10 negative 3. So that's volume flow rate, okay? To be precise, volume flow rate over 17.7 times is 60. So it's equal to 2.35 times 10 to the power negative 6. Okay, so our diameter is going to be 2 times the square root of a over pi, which is equal to 2 times, okay, so our area we calculated is 2.35 times 10 to the power negative 6 over our pi is 3.14. So this is equal to 1.3 times 10 to the power negative 3 meters, millimeters, sorry. So that's the answer. That's the diameter of the wall. Okay. So it is very easy. So in this question, we are going to calculate the minimum pressure that is required for the water to reach the village. So we know that pressure 1 plus density times gravitational force times H1 is equal to pressure 2 plus density times gravitational force times H2. So this is called Bernoulli's equation. So we are going to use the Bernoulli's equation and we've got the data on top. So our H1 is the height of the elevation. So our H1 just simply the height of the elevation 1, which is going to be, or which you have, which is 564 meters, 564 meters. So H1 is called height of the elevation, which is 564 meters. And then our H2 is equal to 2096 meters. So that is elevation 2. H2, let me just write it again. H2 is equal to elevation 2. So elevation 2, okay. So H2 is equal to elevation 2, which is 2096 meters. So the question, what is the minimum pressure to which the water must be pumped if it is to arrive at the village? So we're going to say P1 minus P2 is equal to P1 minus 2 is equal to density times gravitational force times open brackets H2 minus H1 close brackets. So this is the same as pressure 1 or P1 minus, P1 is equal to P1 is equal to 10, and then P2 is equal to 0. So P2 we know that is 0 pascals because there's no height. Then P1 is equal to 10 to the power 5 times 9.8 open bracket 2096 minus 564 cross brackets. Okay, so the height was 0. Initially the height was 0, so P2 is 0, then P1 is equal to that. So P1 is equal to 1.51 times 10 to the power 7. Okay, 1.51 times 10 to the power 7 pascals. So that's our pressure one that I've been told. So that's the answer. So that's the pressure that we're supposed to pump the water at for it to reach the village. So this is same as 15.1 megapascals. So 15.1 megapascals, that's pressure, and that's our final solution. Then our second question, if 4,500 meters cubed are pumped per day, what is the speed of the water in the pipe? So volume flow rate is equal to V is equal to, so volume flow rate, which is presented by V, is equal to area times velocity. So it is area times velocity. So our velocity is equal to volume flow rate over area. So this is equal to 0.0520 divided by 0.017671. So this is equal to 2.947. So 2.947 meters per second. So that's our velocity. So what is the speed of the water in the pipe? So that's the speed of the water. That's the final solution. And please remember to subscribe to my YouTube channel for more videos.